Hello. In this video, we are going to derive an expression for the probability that a particle will tunnel through a barrier. With that in mind, let's define our one dimension, the x-axis, x increasing from left to right. And we can divide this axis into three regions. The leftmost region goes from negative infinity up to x equals 0. The second region goes from x equals 0 to x equals L, and the third region goes from L to positive infinity. We could label these as region 1, region 2, and region 3. An important feature of this particular set of circumstances is that in region 1, we have a completely free particle so that the potential is equal to 0. In region 2, we have a non-classical barrier because we have a potential energy that's actually greater than the energy of the particle. And in the third region, we are again back to a free particle, a region with no potential energy. So we imagine a particle coming from the left-hand side and attempting to penetrate through the barrier and come out the other side. From our previous knowledge of solutions to the Schrödinger equation for the free particle and the particle in a region of constant potential, we can write down wave functions for the particle in region 1, in region 2, and region 3. So for example, the wave function in region 1 we can write as a times e to the ikx plus b e to the minus I kx. And the important thing here is this is a standard free particle wave function, and note that our k here is a small k, which will become important in a minute. So that's the region 1. In region 2, our wave function looks quite similar, but here because the potential energy is greater than the energy of the particle, we have a slightly different form for our wave function. So we have a constant c times e to the big K, there's no I, times x, plus d times e to the minus big K times x. So this is a consequence of the fact that the potential energy is greater than the energy of the particle. Then again in region 3, we have a wave function like the free particle in region 1, where you have f times e to the I small k x plus g times e to the minus I k x. And immediately we're going to introduce a convenience to simplify the mathematics. And we're going to assume that since there's only a small likelihood that the particle will actually travel through the barrier and come out the other side, that there's no likelihood that the particle, having penetrated, would go back through. So that tells us that the constant g is equal to 0. And this will minimize the number of constants that we have to solve for. Another important feature of these wave functions is this constant k. So for a free particle wave function, k is equal to the square root of 2 times the mass times the energy of the particle divided by h bar. Big K has a similar but slightly different form. It's the square root of 2 times the mass times the difference between the potential and the energy divided by h bar. For convenience, we are going to number important equations. So this wave function will be equation 1. This wave function will be equation 2. And this wave function will be equation 3. Since the wave function for the particle must be continuous and must also satisfy the Schrödinger equation, we have a number of boundary conditions. So we notice at the interface between region 1 and region 2, where x is equal to 0, we have that the wave function for region 1 at 0 has to be equal in value to the wave function in region 2 at 0. So this tells us that b e to the 0. We substitute x equals 0 into wave function for region 1, and similarly for wave function for region 2. And immediately we can derive from this that a plus b equals c plus d. Similarly, we know that the first derivative of wave function in region 1 has to be equal to the first derivative of the wave function in region 2. So from this we get slightly more complicated. First, writing out the derivatives, the I small kx minus b e to the minus I small kx is equal to c big K times e to the big Kx minus d big K times e to the minus big Kx. And now we substitute in that x is equal to 0, and that gives us that ai small k I small k is equal to ck big K minus d big K. So it gives us two more important relationships, which we'll number as equations number 4 and equation 5. By the same reasoning, we realize that for the wave function to be continuous, that the wave function at region 2, when x is equal to L, has to be equal to the wave function for region 3 at L. So this is the interface between regions 2 and 3. From that, we get that c times e to the big KL plus d times e to the minus big KL is equal to f times e to the I small kl. So this is the equality of the wave function itself, but we also have to have the derivatives being equal at x equals L. And since the derivatives are equal, we have that c big K times e to the big KL minus d big K e to the minus KL is equal to f I small k times e to the I small k L. Now we go ahead and number these important relationships as equations 6 and 7. Now we have 4 equations in 5 unknowns, so we want to begin to eliminate as many of the unknowns as possible. Our first step is to take our equation 4, which is a plus b equals c plus d. Now we're going to take that equation and simply multiply through by I small k. And once we do that, we get that I small k plus b I small k equals c I small k plus d I small k. So this is a transformation of equation 4. And now we're going to add to it equation 5. which is A I small k minus B I small k is equal to C big K minus D big K. And now we add these two equations together to get that 2ai small k is equal to C times I small k plus big K plus D times I small k minus big K. And now we can divide through each side by 2aik to get that A is equal to C times I small k plus big K plus D times I small k minus big K, all divided by 2I small k. So this gives us an expression for the constant A, which we number as equation 8. Next, we're going to take equation 6, which is C times e to the big KL plus D times e to the minus big KL is equal to F times e to the minus small KL. And we're going to multiply both sides by big K. And that gives us C times. So we've transformed equation 6. And now we want to add to that our former equation 7. So equation 7 is C big K. Now we have minus D K e to the minus big KL. And then we have F I. Now this is small k e to the I small KL. Now adding these two together, we get that 2 times C big K e to the big KL is equal to F times I small k plus big K times e to the I KL. If we divide through both sides by 2 big K e to the big KL, we get an expression for the constant C, which is equal to F times I small k plus big K times e to the I small k sub L divided by 2 big K e to the big KL. And now we have an expression for the constant C, and we number this equation as number 9. To solve for D, we can use the equation transformations we've already used, but now we take the action of subtracting equation 7 from equation 6 rather than adding to it. And if we do that, we get that 2D big K e to the minus big K sub L is equal to F times big K minus I small k times e to the I small KL. And now dividing through both sides, we get that D is equal to F times big K minus I small k times e to the I small k sub L divided by 2 big K e to the minus big KL. And we number this equation as number 10. So notice now that we have expressions for A, C, and D. Our next step is to take equation 8, should call it like this. And now we want to substitute into it the expressions that we had derived for the constant c and the constant d. Recall, for constant c, that is equation number 9, and for d is equation number 10. And to make it clearer, I'm going to color code what we write in for constant c in purple and for the constant d in blue. So we have that a is equal to so that is our expression for c. So divided by 2ik. We can now combine these as the following set of fractions. And this gives us an expression for A in terms of F. Finding a common denominator, we can combine the expressions to get And this is all over 4I, small k, big K.